Hi, Assalamualaikum warahmatullahi wabarakatuh, and a very good morning to the honorable chairperson and my assistant panel of examiner and my supervisor, which is Dr. Nurasha binti Abdullah and Dr. Noridaya binti Muhammad. My name is Nur Adila binti Abdul Manap, and today I will be defending my research entitled Synthesis of 3-hydroxyproline amide base organocatalyst and its application in Aldol reaction. To begin, everyone knows that catalyst is a substance that speeds up the chemical reaction without being consumed or permanently change itself, but it's not eco-friendly because it's using a metal substance. That's why we use an organocatalyst. But what is an organocatalyst? It's also speed up the reaction, but only a mild, and is offering a metal-free that's sustainable alternative to the traditional catalyst. Then, why the Aldol reaction is important? The Aldol reaction is considered a paradigmatic transformation in organic chemistry because it is one of the most powerful tools for the carbon-carbon bond formation, where it's building a molecular complexity. It allows chemists to combine two simple carbonyl compounds to create a larger, more complex molecule that containing both an alcohol and a carbonic group. In industrial and economic utility, the reaction is highly versatile and can be scaled for the production of commodity chemicals such as pentothal and life-saving drug. For instance, a Pfizer initial synthesis of Lipitor, or also known as atorvastatin, is one of the best-selling drugs in history. It relies on a multiple Aldol reaction to build its complex structure. Then, why we use proline amide? Proline amide-based catalysts improve the hydrogen bonding, solubility, and the ability to direct the transition state of the process. These catalysts have been successful in direct Aldol reaction, which yield the beta-hydroxyl ketone and aldehyde. Apart from their technical efficiency, these catalysts are particularly notable in the application of green chemistry in organic synthesis. Moving to the next question, why the chiral catalyst is matter? Chiral catalysts are the architect of the molecular world, guiding reaction to produce a specific handedness of enantiomer. For example, our body is inherently chiral, where our enzyme, receptor, and DNA are made of single enantiomer like amino acid. Because of this, a drug molecule must fit into a chiral biological receptor like a key in a lock. For most famous example of chirality important is thalidomide, where one enantiomer effectively treats the morning sickness, but the other will cause a severe birth defect. So, the catalyst chiral allow chemists to synthesize only the safe therapeutic version of a drug and prevent such a tragedy. Despite the progress in this field, there are several gaps that this research seeks to address. Firstly, there are limited studies specifically focused on the 3-hydroxyproline amide-based catalysts. While proline derivatives are common, conventional organocatalysts often lack the structural stability required for specific substrate. This leads us to our central question: can the modification of proline derivative, specifically at the 3-hydroxy position, improve the catalytic performance? Here is the objective of this research study. Firstly, to synthesize a 3-hydroxyproline amide-based organocatalyst, and to characterize the synthesis catalyst using a FTIR and NMR spectroscopy. Moving on to methodology, the synthesis was conducted in two primary phases. The first phases involved the amide bond formation. We utilized the BOC trans 4-hydroxyl L-proline as the starting material. To facilitate the coupling with the aniline, we employ the EDC HCl and HOBT as a coupling reagent in a THF solvent. These reagents are critically as they activate the carboxylic acid group, allowing for efficient amide linkage without significant racemization. The reaction was stirred overnight at a room temperature, then the crude product underwent a rigorous workout, including neutralization with sodium bicarbonate, extraction with a DCM, and purification via a flash column chromatography using a hexane to ethyl acetate with a ratio of 3:1. Next, on the phase 2, focus on the BOCD protection. The third butoxycarbonyl, which is a BOC group, which served to protect the secondary amide of the proline ring during the first step, was removed using a 1:1 mixture of a TFA and DCM. After stirring for the 3 to 4 hours, the solvent was removed, followed by the azeotropic co-evaporation with a toluene and a high vacuum drying to yield the finally protected proline amide catalyst. Now we look at the result. For the FTIR we obtained, there is a broad peak at the 3564 wave number that confirmed the OH and NH stretching representing the 4-hydroxy group, and the phenylcarbamide linkage was present. And there also an appearance of a strong peak at the 1721 wave number in the intermediate product that confirmed the presence of the carbamate C double bond O from the BOC group. And we also have the primary amide and secondary amide band were observed at the 1641 with number and 1537 with number respectively, that providing a clear evidence of a successful amide bond formation between the proline backbone and the aniline moiety. And we also have a penny ring where they have a CH band aromatic at 1492 with number, and there also a C end stretch and C single bond O stretch, where it represent there is amide group C end stretch vibration, and there is also a ester carbamide linkage in the VOC group. And we also have the aromatic C single bond H that are out of the plane that indicate there is a monosubstitute penny ring, and the aromatic ring band on the 661 to the 673 with number that indicate there is a penny-carbamide ring skeleton. The most definitive evidence for our synthesis came from the 1H and 13 carbon NMR analysis. In the 1H NMR of the protected intermediate, a sharp singlet at the 1.44 ppm was integrated for the 9 proton, that confirming there is a presence of the third butyl group. Furthermore, a signal at 9.13 ppm represented the amide NH proton, indicating successful linkage to the aniline. For the 7.06 to 7.57 ppm, which is a multiplet, this represents the aromatic proton of the penny ring was present, which is there is an auto, meta, and para position. There is also a transition to the phase 2, was confirmed by the complete disappearance of the 1.44 ppm singlet in the 1H NMR and the disappearance of the peak. This proved the successful removal of the BOC protecting group, where you're looking at the 3.27 to the 3.46 ppm, which is also a multiplet. This represents the CH2 group alpha to the nitrogen at the carbon 5 and the CH group alpha to the amide, which is at the carbon 2. They also a multiplet at the 4.56 to the 4.62 ppm, where it's refined signal for the CH alpha to the OH at the carbon 4 after the electronic of the ring change following the deprotection. Interestingly, in 13 carbon NMR APT, we observe a significant chemical shift in the amide carbonyl signal. It shifts from the 172.45 ppm in the protected state down to the 166.37 ppm in the final catalyst. This shift is a direct result of the change in the chemical environment after the protection that was confirmed the electronic influence of the free secondary amide. Let's look at the 154.62 ppm, which is there has a negative. This is the carbamide carbonyl of the BOC protecting group, while the 80.30 ppm, the quaternary carbon of the third butyl group. This signal was disappeared in the final catalyst, that further confirming the protection. The 13th carbon APT was facing for the verify the pyridine backbone, with its the positive CH peak at the 69.96 and 59.21 ppm. That was confirmed the pyridine skeleton was remain intact, and the negative CH2 peak at the 53 and 98 and 38.72 ppm was also intact. And here is all the summary of the discussion from what I have been told about. And now I will be walking you through the mechanism of the amide bond formation. We are starting with the BOC protected 4-hydroxyproline and reacting it with the aniline. Because carboxylic acid are relatively unreactive on their own, we use a coupling reagent such as a EDC and HOBT as a coupling reagent. Our catalyst is bifunctional, where the proline amine activate the donor via enamine, while the amide NH activate the acceptor by the H bonding. For the step 1, for the activation, protonation, and the oxalusuria formation, this process was begin with the activation of the carboxylic acid. First, the acid protonate the EDC molecule. This makes the central carbon of the EDC was highly electrophilic. Next, the resulting carboxylate oxygen attack the central carbon. This forms a high-energy intermediate called an OX lysuria. At this stage, the carboxylic acid is now activated, meaning it's much more ready to react than it was at the start. Now, the OX lysuria is a very strong oxalating agent. Sometimes it's too strong, which can lead to the side reaction. This is where HOBT comes in. The HOBT attack the nucleophile and attack the carbonate of our intermediate. As the electron collapse back down, the EDC part leaves as the stable urea side product. This leaves us with the activate benzotriazole ester. This intermediate is more stable than the previous one, but still very reactive toward amine. In the final stage, our amine, anilines, will perform a nucleophilic attack on the carbonyl of the benzotriazole ester. The HOBT molecule acts as a living group and is actually regenerated to use again. After a final deprotection, we arrive to our product, which is a proline amide. So this method is preferred in the organosynthesis because it gives a high yield and minimizes the racemization or scrambling of the molecule's stereochemistry. Now that we have successfully synthesized our protected proline amide, the final stage is the deprotected of the amide with a solution of TFA in a DCM at a room temperature for about 3 to 4 hours. So, for the step 1, the protonation, the mechanism will begin with the protonation of the BOC group. Specifically, the carbonyl oxygen of the carbamate is protonated by the strong acid, which is the TFA. This makes the molecule unstable and ready for the fragmentation. So, the step 2, the fragmentation and the gas evolution, where it's after protonated, the molecules will undergo a fragmentation process. The bond between the nitrogen and the carbonyl must break, releasing a carbon dioxide as a byproduct. So simultaneously, the third butyl group was break away to form a third butyl carbonation. So because of the carbon dioxide is a gas and leaf the reaction mixture, this step is essentially irreversible, that driving the reaction to completion. And it's step 3, the quenching the cation. The third butyl carbocation is highly reactive electrophile. To prevent it from reacting with our product, the process called alkylation is usually quenched or trapped. As shown in the scheme, it can lose a proton to become isobutyl gas, or it can react with a scavenger or a molecule and to react with and to neutralize the unwanted reactive immediate, that is scavenger. It was labeled as X in the diagram. So it's such a nucleophilic solvent or an additive. This is to ensure that our final amine was remain pure. Finally, we left with our deprotected product, which is 2S4R4-hydroxy and penylprolidine 2-carboxyamide. We have successfully transitioned it from the protected amino acid to a functionalized free-base proline derivative. Now, let us examine the result. The synthesis yield a pale yellow solid with an actual mass of 0.116 gram, and based on our calculation, the theoretical yield was 0.331 gram. That was resulting in a percentage yield of 35.05. This indicating our peak is very low. In conclusion, this project was successfully determined that the synthesis of the 3-hydroxyproline amide-based organocatalyst is a viable and highly effective route for the sustainable and metal-free asymmetric catalyst. The research objective was fully achieved through the definitive structural verification using a FTIR and NMR spectroscopy. The FTIR spectroscopy was confirmed the presence of the essential OH and NH and amide carbonyl functional group, while the NMR analysis provide the evidence for successful deprotection through the complete disappearance of the third butyl signal at 1.4 ppm and 80.30 ppm at the 13 carbon NMR APT. The technical mastery of the 13 carbon APT was facing further verify the integrity of the prolidine ring and the secondary amide linkage, which shift at the 166.37 ppm in the final catalyst. So in the future work, I hope that we can further our study in the Aldol version, because the product that we obtained was very little that we cannot go through the Aldol version. So I hope that in the future we can obtain the large amount of products so we can do the Aldol version synthesis. And I hope that we can expand the substrate scope to include a wider variety of aldehyde and ketone to systematically examine the structure activity relationship and to investigate the recyclability and the catalyst lifespan over the multiple reaction crystals to further quantify its economic and environmental benefit. And here is our reference. And if you have any question, feel free to ask me.